And thank you, Deepika, thank you, Ashish. Thank you, Deepika, for inviting me to give this talk. I'm very happy to be able to give me a good excuse to get up early in the morning. So that was nice. Okay. And so with that, what I will do is, as Professor Garg said, like I came to Purdue back in 2004, and so around 18 years ago. And that time I had a clean slate of PIP, and I had to start my research. So I decided to start in solar, and I will take you through a journey, a little bit of my first few early years. Why solar? I kept asking myself, why not something else? Because that time solar was alien to me. Like I really had no experience in solar research, and yet I picked it up. So I will just take you through a couple of early slides, why solar, and then I will make a transition to, after I decided solar, then I realized that it is not an easy game. Okay, there are a lot of challenges. So I spent the next few years learning about the challenges, and then I will just give you some of my flavor of some of the research actually. With that, so why solar energy? Because and so what happened was in early days when I came to Purdue, I beginning to look at, for example, if you look at the human population over the centuries, what you find is that the human race, give me a second. So what you're going to find is that the human race population was more or less, dwindling along, was going along. And somewhere the human race lived for a long time, all renewable resources, and somewhere along 1700 or so, the human population began to really take off. Okay, and so the issue was why did it suddenly begin to take off? And it's no secret to us. This was all because of the rise of coal, okay, and the discovery of the steam engine. Because what happened was that suddenly people did not have to rely on oak trees, okay, or the twigs as a source of energy. So biomass was the primary source of energy has been for most of the human existence till the coal was started being used, and suddenly people could fill the buckets and buckets with large quantities of energy, and then the steam engines came along. And so Sadi Carnot, trying to explain the steam engine, he came up with the laws of thermodynamics, and suddenly there was an explosion of the human race, which has been unparalleled actually. So the fossils have been a friend of human race. I think the fact that I can give this seminar is itself a tribute to the fossil energy. And so they have been friends, and they have been here. But the question is it is leading to two things actually are primarily responsible for it. First is that fossils cannot last forever, right? Because the rate at which we consume energy far exceeds the rate at which it is being formed. So sooner or later, it's going to happen. And sooner or later, I mean in the context of the human civilization. So in the year 3000, as we move to the right, okay, and keep going thousands years from now, we need to think what the human race should be living actually. And so the question is how long this fossil will last, besides the environmental pollution, which I would not be touching. So it became very clear to me at that point in time. Eventually, at some point in time, human race must transit from the fossils to the renewable source of energy. And whether it is in 2100 or 2200 or 23, whatever it is, but it has to happen because humans will be here for 3000 years from now, actually. So having said that, so what could that energy source be, right? And of course, for a sustainable world, that energy, I realized that it has to be a solar energy. And so once we realize that it has to be solar energy, then okay, yeah, so it has to be solar energy. So once we realize that, so it has to be a solar economy period. And why solar? Okay, the reason being solar is because the fraction of the solar incident irradiance which Earth uses, okay, is very small. So for example, it is 3.8 million exajoules a year of solar energy which is falling on the planet Earth. And we use only roughly 530 exajoules. So it's a pretty small fraction. So it is the most abundant energy source that at almost every place on the Earth, almost, not every place, but almost all the place gets the solar energy year round. So it's if we learn how to use it in everything in our daily life, then I realized that, okay, all right, so that's what can be a more meaningful research. And if it did use solar energy, then You can almost do everything, even, and I'm a chemical engineer, as Ashish told you. And we can make all the chemicals, okay, we can heat everything, we can produce the electricity, we can have mobilities, and of course the food, which comes from the solar energy. The solar energy can meet almost every need which we have as a human race, which fossils meet. And therefore, certainly solar is a very attractive option. Okay, so if that is the case, then why is solar use not that prevalent, even though it has been rising lately for the last 5 years or rather 10 years, but back in 2004, 2005, it was like, why is the solar use not prevalent? So I spent like 2-3 years just thinking about that, and so I will just share with you some of the challenges which I understood at that, and I still continue to take it in that context. Okay, and so the first thing I realized was that the solar energy is quite dilute as against the fossils, which are quite dense. And what do I mean by that? And what I mean by that is, if you look at, like, when I go and fill my car with petrol, and I can fill something like 10 gallons of petrol, like, you know, in a minute. Okay, and that's like 20 megawatts of power supply. So the rate at which I'm filling in my car, as you can see, is quite high actually, right? So 20 megawatts is quite it's like 20,000 homes could be powered for during that period. Okay, so the question is, if I needed the same amount of power from sun, what will it take? And of course, solar incidence is roughly a kilowatt per meter squared. So if you use that, then what would mean is that if you wanted 20 megawatts of supply, I would need 4 soccer fields, roughly 4 soccer fields, which is the area of 20,000 meters square, to supply the 20 megawatts of power. And that's assuming 100% efficiency, but as we know, there's no such thing as 100% efficiency. And therefore, like, you know, if the efficiency was 20%, then you would need 20 soccer fields. And any one of us who have gone to watch soccer game, we can imagine, like, you know, 20 of these soccer fields and how large that area would be. Whereas, you know, I could fill my car like in a bucket, like, you know, within no time. So it gives a feel for how dilute the solar energy is, and which is kind of a good thing, right? Because it is dilute, so we can go out and we don't get burnt. But from an engineering perspective, our raw material, or whether our raw energy supply, is very dilute, and that has repercussions. Because what that would mean is that to get certain amount of energy, like, I need a very large land area, and the equipment used for collection also must be very low cost, right? Because I'm recovering a very large amount of area, and if the cost per unit area has to be very, very low, otherwise it will not cut it. And the second problem was that which I also quickly realized, is that the energy on top of that, not that for a given amount of energy, not only we need large area, but the amount of energy we use is also quite large. Okay, like, for example, for United States, this is 100 quads, and the quad is 10 power 15 BTU, and 1 BTU is roughly a kilojoules. Just because the United States, people do live in old energy units, but so BTUs, think of it as kilojoules for today's discussion, and that is equivalent to 800 billion gallons of gasoline equivalent energy. And what that means in the United States, every human being who lives in the United States is consuming on an average of 6.7 gallons of gasoline equivalent every day, and I don't even drink 6.7 gallons of water every day. So it gives a kind of a feel, like I was telling you about 10 gallons per unit time, and each individual in the United States is every day, by the time they wake up and they go to bed, they would have consumed close to 6.7 gallons of gasoline equivalent of energy. So it's very large, okay? And India's energy use, for example, in 2020 was a little bit less than 2019, but nevertheless, it was 37 quads. So just to give you a feel, like, it is roughly 40% of the United States total energy used in 2019. So it's still quite large, even though it is, given the population, it is quite low, but nevertheless, it is quite large. Okay, so the energy use is very large. And what that means is that one has to cover large land area actually to recover the solar energy. And for example, for UK, I will show you later, it could very well be UK and Germany. They might have to cover 25% of their land area if they were to supply all their energy by using solar energy. So land constraint implies like how you collect solar radiation will play a very vital role in the future of the human civilization. And to top it off, solar energy is intermittent, as we all know. Like in most part of the world, it is available only 20% of the time, and India maybe 25% of the time. But certainly it is a very small fraction, and so it needs storage. And also not only storage. The second problem is as engineers, whatever plants we build, like it works 24 hours. Like if you build a steel plant, or if you build a cement plant, or if you build a petroleum refinery, they work 24 hours. So the return on the capital is continuous, whereas here the return on the capital is only 20% of the time. So if I build a photovoltaic farm, like and if I sink my capital, 80% of the time it is sitting idle, making no product. So what that means is there's a further cost constraint besides needing the storage. So those are quite the challenges. And now I'm going to switch, and I'm going to then after that I will just give you a journey about my research with the biofuels, and I will give you a different context of it. So that time I was thinking how to harness solar energy, where should I go, what problem should I tackle, and then I realized that solar energy can be harnessed in several forms, right? So you can grow biomass, you can make hydrogen out of it, you can produce electricity, you can use concentrators, produce heat. So what I did was I was debating where should I focus my research. So I began to look into all those 4 areas, and what I realized was that if you look at the solar photons, and if you're looking at the energy recovery from it, electricity can be recovered at very high efficiencies. Like today, you can buy PV panels, which could be close to 20% efficiencies. And of course, if you use concentrators, you can get, and if the solar radiance were direct, not diffused, and then you could collect it at a very high efficiency at very high temperatures with very high exergy contents. And of course, if you can make electricity with 20% efficient, electrolyzers can make 12% efficient hydrogen. But to the surprise of me at that point, but now I know it fairly well, but that time that the efficiency of the biomass was roughly 1% for harnessing solar energy. And sugarcane, ganna in India, which is one of the highest efficiency, crop. Okay, even that has the efficiency of close to only 1%, in the neighborhood of 1%. And so what that means is that if I'm growing biomass as an energy source, okay, I would need 10 times the more land area actually, because even 20 times the more land area. And I already told you that solar energy is dilute, and even with 20% efficiency, we need large land areas. So it became very clear to me very early on to focus on biomass as an energy source for the long term, even though for the majority of its existence, human race has lived out of biomass, but that's why the population was small actually. And of course, if I took biomass and tried to make a liquid fuel out of it, the chemical process of conversion has 50 to 70% efficiency. That 1% becomes even 0.5 to 0.7% efficiency. So the biomass to liquid fuel did not look like a viable option. So I thought that, but nevertheless, I will is the order of magnitude less efficient biomass is, okay. And so if you wanted, there were a lot of biomass will be needed. So I did a couple of calculations that time, and I will quickly share results with you. Is if you look at what I call sustainably available biomass. So what is sustainably available biomass? Basically, SA biomass is like, for example, if you're growing ganna, then from ganna you can, after the juice has been collected, the bagasse which is left behind would be a SA biomass, because you're not using extra fertilizer, you're not using extra land, you're not using any extra resources to get to that biomass. And could that biomass be converted to liquid fuel? And if yes, what would you get? In the United States, it will be the leftovers after the corn kernels have been collected, and so forth. Okay, and so calculation shows that if we take SA biomass and we converted it to liquid fuel, or any chemicals, let's call it fuel for the time being. And if you use the standalone processes where biomass comes and it is converted just like sugar to alcohol or whatever have you. And what early modeling research showed to us was that no matter what process we used, whether it was gasification, Fischer-Tropsch, fermentation, hydrothermal gasification, pyrolysis, hydrotreating. So we model all those processes. And to our surprise, that all those processes recovered only 40% of the biomass as liquid fuels. Okay. And liquid fuel, I mean molecules which have the same energy density as gasoline or diesel, and meaning they are free of oxygen, and only 40% of the carbon was recovered, and the rest of the carbon, meaning 60% of the carbon which came with the biomass, went back to the atmosphere. Okay, and so the question was like, okay, so in United States we have SA biomass of roughly 500 million tons per year, and the transportation fuel use is roughly 30 million barrels a day. And if we took all this 500 million tons of year per year of biomass and converted it to gasoline, it will be roughly 2 million barrels, which is a very small fraction of like 30 to 40 million barrels. So certainly, if we were to rely on biomass, like liquid fuel will need a lot more liquid fuel than a lot more biomass than is available sustainably. And so, but before we do that, I already told you that heat and electricity and hydrogen could be recovered by an order of magnitude higher efficiency. So rather than growing more biomass to make liquid fuel, like we asked a question that why not? So why is that carbon recovery 40%? The recovery of the carbon is 40% because biomass has 35% oxygen, and what that means is the energy per content of carbon in a biomass is roughly roughly like I would say like it's only 60% of the energy which is per carbon atom in the gasoline or diesel, right? Because there's no oxygen there. Those molecules are not partially oxidized. So in the process of conversion, what we're doing is we're increasing the energy content per carbon atom. And since we're increasing the energy content per carbon atom, the first law tells us is that if we want to preserve all the carbon which came with the biomass and have to show us, we have to supply energy to the system. And the best way to supply energy to the system is what is recovered at higher efficiencies, such as electricity and hydrogen, and so that we have additional energy to store on the backbone of carbon and produce the fuel. And so this way, 100% of the biomass carbon recovery would be possible. And we did a lot of experiments and we published a lot of research in those days. And that was like taking biomass and taking a hydrogen from a carbon-free source. We did a lot of experiments, and time does not allow today for me to go in details, otherwise that could itself be an hour talk. And so I'm going to just let you know that we did experiment with fast hydropyrolysis and hydrodeoxygenation with my colleagues at Purdue, and we produce alkanes directly from the reactor actually. And the CO2 was recycled, and hydrogen followed by catalytic deoxygenation upgraded the fuel. And the goal was not to release any CO2 back to the atmosphere. So biomass carbon, we learned very quickly, actually I learned very quickly that biomass carbon can be used for chemicals, but we better not use it for energy because that will be a losing game in the long run. Especially use of biomass to produce heat or electricity or hydrogen is not sustainable in the long term in the context of the energy used by the human civilization. And also, like if we imagine like we say that the carbon content in the atmosphere is very high because of the environmental warming and so forth, but that concentration is only 415 parts per million. And as a chemical engineer, to me, 415 parts per million is very low concentration if I'm going to recover it as my feedstock, because the way I imagine is as I was taught in my undergraduate in L7 is that is if there are a million molecules passing by me, and if all the molecules are green in color, and there are 415 molecules which are red in color, and if someone gave me a beaker and a forceps, and if my job was to catch those 415 red balls and put it in the beaker, okay, I would get bored actually, basically entropically very unfavorable process. And what that means is that, but Mother Nature has done exactly that. It captured those 415 red balls and gave me in the form of leaves and wood and twigs and so forth. And therefore, to put it back in the atmosphere is absolutely not justified. So the way I look at it is, biomass is a carbon source, not an energy source, and we should make use of that carbon to produce chemicals and so forth. Okay. And the other thing which I realized by the same token, okay, as you can see from a running thread so far, that hydrogen and electricity could be recovered at much higher efficiencies. And the major thing is that if we took biomass as a carbon source, then what that means is that biomass can provide the carbon, and the hydrogen and electricity, along with the heat, of course, can do almost anything we want, right? Because we can make fertilizers, we can make urea, we can make ammonia, we can make almost all the major chemicals which the human race uses, okay, and cooking and purification of water, mobility, energy storage. So there's a whole slew of things which can be done. So I decided that I'm going to focus on the electricity in my research, okay, and this is how I reached to my conclusion that that's the fruitful area where, as a chemical engineer, I could go in and begin to focus, and that was so I decided to start my research in solution process solar cells, even though that point in time that subject was quite alien to me, but I figured that that was the right thing to do. So I began to look at the solar cells, and as I began to look at the solar cells, like, I realized, like, so I'm going to could use one of them as an example where I have focused a lot of my time, which is covering in gallium diselenide. Of course, a solar cell is a thin film device with multiple layers and having an electric field inside. Light is absorbed, holes and electrons are separated, they run outside under the influence of electric field, and the circuit is over. So I started to focus, and absorber is the place where most of the light is absorbed, and the electron and holes are created. So I started to envision my research focusing on the low-cost absorber layer. And for the low cost, like even today, the world's most of the solar cells are not produced by printing. So how about, given my background in chemical engineering, I decided that maybe I should formulate the inks to print on a roll-to-roll solar cells for different layers, like in this case, copper, indium, gallium diselenide, let us say. Put the absorber layer, come along, put the cadmium sulfide, the N layer, intrinsic zinc oxide, put the transparent conductive oxides, grits, and so forth. So I started to focus on the printed solar cells and solution process solar cells. And I gave Deepika a choice that should I talk on the, I could have given you a very easily, multiple hour talk on the solar cells. I would love to talk about it because this subject is quite near and dear to me. And when Ashish visits us, I will probably bore him a little bit through my lab and what research we are doing on this subject. So, but anyway, the bottom line is we are focused primarily on the absorber layer. And in my lab, we take two approaches to make solar cells. First is we make nanoparticles, we suspend them in the ink, and we print them, and when we deposit it, we heat it, and we have multiple coaters in the lab, and then we have a cross section of the nice thin films of the semiconducting materials. Then we can grow large grains, we can finish device, and we can measure their optoelectronic properties after that. An entire thing can be done in my lab, actually, from the left to the right, including the material as well as optoelectronic characterization of the materials. And the second route is where we don't make nanoparticles, we directly dissolve the molecular precursors. And in this case, we could dissolve, for example, copper sulfide, indium, gallium directly, and selenium directly into the solvents. We discovered some solvents which can do that, and we can print and print the device. And from my lab, we have, to this date, to my understanding, my lab holds the record of the highest CIGST efficiency from the nanoparticle inks, okay, which is 15% total area and 16.2% active area efficiency. And still it is from the nanoparticle ink, that is still the highest efficiency. But for the last 10 years, the lab is also focused on making cells from the earth abundant materials, like example, copper, indium, gallium. Indium is not as earth abundant. And in that spirit, we have focused quite a bit early on, we focused on copper, zinc, tin, sulfoselenide solar cells. And though Sarang is also busy with doing copper, zinc, tin sulfide solar cells, and we also did back in 2009, we started a research on that. And we made a lot of progress. We made 9.3% efficient solar cell very early on. And however, this material is inherently defective. And I would not go into the reasons why it is. We did a lot of analysis, and to our disappointment, we did find that it is quite defective material, and therefore we have stopped working on it as of today. And but we tried many materials that time. Actually, we doped it with germanium, we alloyed it with germanium, we doped it with silver, we alloyed it with silver, we made copper arsenic sulfides, and then so forth. Lately, my lab is involved in making chalcogenide perovskites, okay, and by solution processing, such as barium zirconium trisulfide, barium hafnium trisulfide. We are pretty excited. This is a very new thing in my lab. We have done in the last 1 year, and we have succeeded in making them. So we are thrilled actually, and because these should be stable as against the halide perovskites, and early indications are yes, they are stable. So that's where half of my lab is focused right now, and so forth. Okay. And the search continues, okay, and in the remaining time, I will visit back the land constraints. So while we are doing all this research, it kept bugging me, and I visited with Manju, my wife. Actually, I visited Kerala, and we went to the Munnar Hills, and probably one of the most beautiful places I have been to. Looking at those tea gardens, and both of us were standing there. And I was lost in the beauty of the nature, actually. And suddenly a thought came out of nowhere that such a beautiful place, and if they needed electricity, how would they do that, actually? Because those hills are rolling hills, and lovely scenic hills, and there's no place to be done because that would hurt them. And on the journey back, when I took journey from New Delhi back to Newark, I spent the entire time on the plane thinking about it, drew a lot of schemes, a lot of photovoltaic cells, so the question I posed to myself during that trip, during that so-called vacation or holiday, whatever you'd like to call it, is that how would Munnar get its electricity, and how the photovoltaics could play a role. So that started my electric farming, introduction to electric farming, so that was like 2015 when I had visited the Munnar Hills. And so after coming back from there, began to look at what is the actual, by this time, by 2015, there's enough solar farms which have been built in the world, so PV, and what is their electrical output, right? So what this shows is power per unit area from solar farms around the world. There's a lot more data if you go to the source there, and you can find more source from the National Renewable Energy Lab in Colorado, all over the world. But just for the illustration, this graph, I intentionally took out a lot of points, and there are only a few points which are shown. So let me tell you what x-axis is and what y-axis is. So x-axis is the solar irradiation insolation, okay, and as you can notice, it runs only up to 220 watts per meter square, as against the 1000 watts per meter square, which I showed you earlier. The reason for that is because this energy is on a 24-hour average, not instant average. So, and since sun is out only 20% of the time, so what happens is that 1000 watts becomes 200 watts. Okay, so it is based on the average, because the logic here is that we as a human race use energy 24 hours. And therefore, let's talk on the basis of 24 hours rather than when the sun is out, okay? And same thing, power per unit area. So basically how much power is produced based on the unit area of that solar farm, okay? So the solar insolation, meaning how many watts per meter square based on the 24 hour. Same thing, power per unit area based on the 24 hours, because some of you must be wondering why 10 watts looks very low, but of course it is, remember, it is 1/5 of what it would be if the sun was being had. And you can't cover all the land with PV, because there are a lot of land which is wasted, because you can't allow the land to have shadow from one to the other. And with that, what you find is that the northern places like UK have very low power per unit area, like 5 watts per meter square. On the other hand, in US is all kind of variations. But the bottom line is, what you find is that the solar farms in Northern Europe is roughly 5 watts per meter square, right? That's what we saw. And southern, like Spain, which is India, will be somewhere here, I would say, more like India has its own challenges with PV, which we can talk later on. But between 7 to 10 watts per meter square could be India, okay? And of course, the United States, we have all the way from from 5 to 11. So the maximum is around 11 watts per meter square, and average is around 7. And most of the places in Northern Europe will be 5 watts per meter square. So why do we need those numbers? The reason we need those numbers is because once we know what's the power production from a solar farm based on a unit area for a given country, then what we can do is we can ask how much power they are consuming based on their total land area, right? So we know how much energy is consumed in a year, and therefore we can calculate on a 24-hour basis. We can translate how many watts that is, how much power that translates into. We know the land area of that country, and therefore we can know how many watts per meter square of that country of the energy is being consumed. So if you look for UK and Germany, what you find is their population consumes roughly 1.25 watts per meter square equivalent of power. And if the solar farms are producing only 5 watts, that means these countries will have to recover 25% of the land area. Okay, so that's not going to happen. There's really no way that a 25% empty land is available in a country, in a densely populated country like UK or Germany, in fact. And how about India? Okay, so last night I did some quick calculations for India. As a matter of fact, I have a graduate student from IIT Kanpur, like Subhanshu, and he has done a lot of extensive calculation. Actually, I have to encourage him to publish this paper, which is my fault. Actually, I have not done that. But what you are going to see, which one of my graduate students did in the context of the United States, when Subhanshu arrived last year in January, he took one of my classes and he did those calculations, and I need to along with another student like Catherine. So both of them have done for India. But nevertheless, last night I quickly did some my own math, and India's power requirement is roughly 0.375 watts per meter square. And if you look at the land area and the total energy, that means 4% of the country's land area must be covered with solar farms if India wants to meet all its needs with the solar energy. However, I have to caution here, this 4% is really not the number, because India's per capita energy consumption as of today is roughly 1/10 of the world, or half. So what that means is that as India continues to move, eventually its energy consumption catches up, okay? And if it doesn't increase by a factor of 10, certainly it will increase by a factor of 4, okay? And so what that means is that 4% could become 15 to 20% of the India's land area. So remember, we are not talking of tomorrow. We are not talking 20 years from now. We are talking 1,000 years from now. Okay, so this is for the human civilization. How the human, all of us who are transiting from this planet, we are here only for a short period of time, and we need to think in the context of the human civilization and the time period at which, from as we travel through this planet actually, and so the consumption. And how about the US? Okay, so US average power requirement is 0.43 watts per meter square. And what that means, just like India, like the US will need 4 to 6% of its land to supply the PV. But let's closely examine it. What are the repercussions? So of course, the United States is a bigger country, and most of the solar energy is in southwest of the United States. Okay, and most of the other parts of the United States don't have such a high solar irradiation. So what that means is we will have, in the United States, one will have to produce the energy in one corner of the country and transport it to the other corners. And that would require trillions of dollars of investment, and high voltage grids will be needed, large investment in the infrastructure. But the question is, can we take advantage of the fact that the solar energy is everywhere, right? So local photons for local use, okay? So what this allows us to ask ourselves the question, which is very different from the fossils, which would move around with the tankers and the rail cars and so forth around the world and within a country and the pipelines. But the solar energy is locally available, and what are the repercussions of that? Okay, so we began to look into that, and we began to look. This was again like after coming from Monarch, that was one of the early days, and so we started to ask those questions and did calculations. And I look at the clock, so the time is running. So I will go a little faster. But to sum it up, what we did was we just can't take the total energy a country is consuming and translate into the solar energy just the way I showed you earlier, because in the fossil world, the way we use energy, and we all are familiar with the second law of thermodynamics, right? So when we transfer it into electricity, there's something called Carnot efficiency. So there's only a certain fraction of the energy being used, constructively used actually, and a lot of it is wasted to the atmosphere. Whereas in the renewable world, we are already getting electricity, which is the highest form, which is exergy equivalent actually. So So we can't take 100 units of energy in a fossil and put it 100 units of electricity. That would be like comparing apples with oranges or mangoes with amroods, okay, with amrood or whatever. Okay, so we need to look at it a little bit differently. So what that means is in the current system with natural gas and petroleum and coal, we meet all our needs. And in the future world, by the way, I'm not talking about wind here. Wind is implicitly included in the solar, okay, just to keep my talk simple. So I don't want anyone to say that we have bias against wind. Wind will also play a big role, but wind is not available everywhere. And since solar is available everywhere, that's why I have been focusing on solar so far. So with the elements of solar, water, and biomass, water for the hydrogen, biomass for the carbon, solar for the electricity and heat. Okay, if we go that, and we can look for every need we have, and for example, for the light duty vehicles for cars, what we can ask is how much petroleum or gasoline is being used, okay, to drive a car. If the internal combustion engine has a 15% efficiency, we can calculate what is the actual energy output constructively used, and then we can do the same thing for solar. If we produce electricity, what are the transmission losses, like 4.7% transmission losses, storage, motor efficiency, and 75% use, and then we can equate the two, and then we'll know for every 100 units of petroleum, how many units of solar energy would be needed. And we can do those calculations for all the sectors, from residential, chemical production, in-house industry, and so forth. And this is a very detailed calculation. And then we can conclude that total end power use is United States is 665 gigawatts, which is the end use, okay, which is not the fossil, but this is what the solar energy will have to supply. Now that solar energy has to supply all that, what does that mean? So if you look at in the United States, I told you 4% of the land area might be needed, but now what happens is the urban land area in the United States is 3.2% of the total. And the miscellaneous land area, meaning deserts, barren land, and so forth, is roughly 3.6. And the agricultural land area is 54%. And land area for the special use is 9%. Forest use is 30.4. So what do we learn from here? What we learn from here is almost the entire land is agricultural land and the forest land, right? Okay, and of course, no one would like to destroy Yellowstone National Park or the Grand Canyon for that matter. Okay, or in India, for example, Rajaji's Park, or the Munnar Hills, which I just talked about. Okay, those are the areas you really don't want to touch. Those are the national, what I call jewels. Okay, so what that means is that the land area which is really available is quite low. I don't know today about IIT Kanpur, but when I was an undergraduate at IIT Kanpur, from the campus, if you walked out of the campus, it was all farmland area. Actually, it was all khet after khet after khet after khet. There was no empty land. Okay, and so my recollection of that era is that, and even today where I live, like outside, so in winter it might look like an empty land, but by the time Ashish arrives, all around when we'll see it, it is all corn and soybean. Okay, so there's no empty land per se. And so the area which is available to put the photovoltaics is either in the cities, in the urban land area, or the miscellaneous land area. And there are many studies which have been done to see what fraction of the urban land area you could use for PV. And by various measures, it is between 1% to 12%, because you can't put PV everywhere, and they cast shadows, and it has to face sun, and there are many constraints. And of course, the miscellaneous land area, the same thing. So we did some quick calculations under many scenarios, and I will share with you one scenario. So if you were to use 5% of the urban land area for solar and 50% of the miscellaneous land area, then how does the picture look for each of the states? Because remember, it is local photons for local needs. And since we're looking at the local, so we did calculations. We did very extensive calculations as to if every state, I live in the state of Indiana right here, okay, and so if Indiana wanted to meet all its energy need by its local solar energy, what will it take? And if you were to build the farms, so if I took 5% of the urban land area, and if I took 50% of the miscellaneous area, what power output would I need from my solar farm? And that is more than 11 watts per meter square. Okay, and I told you earlier, the most solar farms don't produce more than 11 watts per meter square. So what that means is that I don't have enough land area. And so United States, if local energy is to be met, 24 of the states will require more than 11 watts per meter square to meet their local energy need. Okay, and what that means is that 24% of the states do not have enough land to meet their local energy with the solar. So So what does that mean? That means if they wanted to meet the local energy need with solar energy, they will have to put these PVs on the agricultural land area. So there's a competition between land between food and energy. And of course, people like me will rather have my food. I would rather have my rice and sabji rather than the power to my iPhone, right? So, well, that's a joke because we need both in today's world. But so the catch is, if you were to put in the agricultural land, what fraction of the agricultural land would be used locally? And we did a lot of calculations for that. And for example, the state of Indiana, where I am, okay, they will end up using roughly 15% of the land area of the agricultural land area, which is a smaller fraction of the land area, but nevertheless, one is going to be using PV in the agricultural land. But if we did that, it can meet all the land area. And the situation would be quite similar for India, by the way. Okay, I think especially 100 years from now, as India has moved and its energy consumption per person has gone up, like, it is bound to happen that way. And so that got me into eclectic farming. Okay, so that was like 2000. So it took us a year for my graduate students to do the number crunching and do the modeling. And then after that, we decided, okay, we're going to take this and start doing a research. So what I call agriculture and electricity production eclectic, PV eclectic, because it is PV. You could have wind eclectic farming, you can have PV eclectic farming. And so what's the challenge? The challenge is, if you put photovoltaics on agricultural land, they cast shadows, and the photosynthesis activities, it is the same visible part of the spectrum from 400 nanometer to 700 nanometers, which is, I learned very quickly, it is exactly the same spectrum which our eyes use, is the same spectrum which the PV use, which the plants use. And that's not a surprise, that's the maximum in the solar radiation from the sun. So over the evolution of the planet Earth, like all the species have evolved using that maximum wavelength, like the photons in that window with the maximum concentration. And so for the farming, for example, like, you can see here, these panels are casting shadows, and there is a output decline actually. So like showing current PV designs, conclusion is they cast shadow, and the crop yields, and the 10 to 20% decline in the food production would be tremendous actually. So what we did was, we did a lot of calculations, which I'm not going to bore you with, like how the PV panel should be mounted, what their shadows look like, dynamic shadow versus the static shadows, and different designs and so forth. And the upshot is, in the interest of time, is that we did build it. We went ahead and we Purdue is not only a big engineering school, but we are but Purdue is a big agriculture university also. And so what that means is that we have a lot of colleagues in agriculture department who are world-class agronomists. So I knocked on their doors, and some of them were kind enough to come forward and collaborate. So Purdue has a big farm, which is farmed under actual agriculture practices. And so we did install these east-west tracking panels, which are 20 feet high in the air, in 2019. So it took us 3 years to collect money and build these things. And here it is, we are growing corn, and east-west tracking, as you can see, corn at the bottom, which is all lined up actually. And by November, we have snow. We were talking about the weather earlier, it does get cold by that time, but the plants are harnessed. The point I would like to tell you, it's very laborious. We collected individual data throughout the plant, 1,500 to 1,800 plants, 1,900 plants. Every 2 weeks, students went in, collected their height, leaves, silking, antices, dates, and when did they crop up, how their height changed. Corn ears were collected individually, how many corns in the kernel, what's the density, what's the yield. Very laborious job, but we have done it for 3 seasons. Quickly showing you the data. In 2019, we were very late in planting. We planted in June, so we had to plant a hybrid seed, which was for a small season. And what we found out was for those seeds, the shadows did not matter. The yield was roughly the same. Okay, average yield was roughly the same. However, in 2020, we planted the normal seed, okay, which for the long duration, and we found a 8% decline in the yield without PV and with PV. So there is a decline, and we are doing a lot of modeling right now. And with that modeling, we are trying to understand how to increase the electrical output without hurting the yield from the plant. And hopefully in 6 months or so, we will have our early results for publication. So what's the vision here? The vision here is, of course, you got the agriculture farms, okay, and you got the PV panels, and you got the wind farms. and you produce electricity, and biomass gives you the carbon source. You make hydrogen, and then you can produce locally chemicals, distributed plants. Chemical engineers have to rethink what they're doing, and similarly, the material scientists who are in the steel production, cement production, metal production have to rethink how they purify the metal without the coke and with the help of electricity. We have to reimagine the entire manufacturing sector. We can locally produce, and then we can locally have the needs being met, okay, for the pure water and so forth. Basically, distributed plants and on a small scale, and meeting local needs with local solar energy actually. So that sums up where we are today. Okay, so I think for a sustainable future, we have to learn how to use solar energy. And it provides a lot of unique opportunities to us, because suddenly we have local photons and local energy source which we can use to meet local needs. We don't have to rely on different nations to give us the energies. And however, there's a lot of challenges as we discussed. And I think in my mind, the primary challenge is the solar energy being very dilute, meaning very large areas would be needed. And then coupled with its intermittency and storage, like both of them are probably the single most challenge. And I do believe that if we learn how to make electricity and hydrogen in an economical fashion from this, and learn how to store them, like we can do anything what we have learned to do with the fossils. And because of the dilute nature, there is a land constraint and competition with the agriculture, and we must begin to solve that problem today rather than leave it for the later time. And what that means is someone like me who's in chemical engineering, and I'm sure it is true for most branches of engineering, except maybe the electrical engineering, is that once we have this, okay, how do we do all the things we have learned to do with fossils? But we do with the renewable electricity and hydrogen. And what that means is reimagining all the processes, the steps, and how the things have been done. And so that's how I look at this very exciting scenario, actually, because I find this very fascinating. And with that, I would like to finish my talk, thanking all my guidance friends and the team, and they are the ones who really cranking the output, and I get to present it. And with that, thanks to all of you. I know it's late in the day, and listening to me patiently, and I appreciate that. Thank you very much.
Thank you, Dr. Agarwal. It was quite an interesting presentation, and we all enjoyed it a lot. So we thoroughly enjoyed and got to know a lot of new concepts which we were not aware about earlier. So thank you so much for delivering such an interesting talk. So now from the audience, I would request like whosoever has the question, they can raise their hand, then one by one we may ask them to pose their. Kindly raise your hands. Yeah, Jitendra, you go ahead, please.
Thank you, Professor Agarwal. It was really a wonderful talk. I just wanted to know your views on the material, like who actually can compete with which material can compete with the silicon. Like for example, CIGS and CDT, they were able to get to 20%, which is good for a commercial application, but still we do not see. Like, do you really see any material which can replace the silicon, or actually can challenge to some extent to play like some market share?
So that's a very good question. By the way, silicon is very entrenched, and 95% of the solar cells are silicon, and they will continue to be like that. But however, I do believe that other materials can challenge. That's why thrust of my research. So regarding CIGSC, the problem. So CIGSC in the lab have achieved 23% now. But the problem with that is the manufacturing problem. Like it's very difficult to get CIGSC uniformly over a large area substrate. And so what that means is the inhomogeneity on the surface of as copper, indium, and galliums are deposited, like with selenium, leads to variability in the efficiency. And what that means is the net efficiency is much lower. And that's the reason for it not competing with silicon. But on the other hand, cadmium telluride competes with silicon, but it has its own challenges, right? Some countries don't like cadmium because of being elements of poison. We see tellurium is very null, like the metal. So that also produces a constraint, but cadmium telluride, first of all, can produce with reasonable efficiencies, and it can compete in cost with silicon. But you're absolutely right. Like, so silicon is entrenched, and so the day, like, halide perovskites could have competed, but they're unstable right now. So that has been their Achilles heel. But sooner or later, if they solve that problem, they could compete with. I think they could compete with silicon. But I do believe that the search continues. Let's see what happens. And that's why I'm working not on chalcogenide perovskites. Early indications are their optoelectronic properties are quite good. And now, but it comes with those backs of challenges, so as those are crossed, and hopefully we will come up with some.
Professor Gautam Dev, you have a question?
Yeah, hi Rakesh. This is Gautam. We meeting after a long time.
Yeah.
So always I get interested. Unfortunately, I wasn't there in the beginning of the talk, but when you came down with one of your conclusion is that you have to have in a quantum of land area, you have to distribute your energy production, your chemical production, your living. Do you have any idea how what fractions of these would be an ideal setup, or is that something still being worked out? It depends upon the efficiencies of each, and that it's a bit more complicated than but a rough thumb rule which you would.
So like it depends on the crops, like and I showed you, like even for the corn, like 2 different seeds give 2 different performance, and so but the thing is kind of like we're doing a lot of detailed modeling right now. We're using EPSIM, which is the crop model, okay, and we're using EPSIM for crop model for the corn. But in the Indian context, if it is rice or gehu, then what that would mean is like we'll have to do their EPSIM calculations and see how the shadows are interacting with the light intensity. So things which we are studying right now is what part of the growing stage of the plant we can steal more photons from the plant, okay, or what time of the day we can steal the photons so that the plant still gives us the same yield as it would give without that. So, and also this is also what kind of PV panels should we design and install, and how do we track the sun or untrack the sun, let's say both, okay, during the daytime. So it's quite an interesting research, let's put it this way. Okay, understand the photosynthesis in coupled with the PV part is the easier part. It is the photosynthesis part, how to make sure the plant goes through all their stages. And of course, it will be different for different crops. So right now we are focused on corn, and last year we did some soybean. And because I live in Midwest, and that's where those are the only 2 crops, it's not wheat or it is not rice. So, but nevertheless, like in Indian context, like I think the similar research needs to be done in detail with the EPSIM modeling and so forth. And so we are still trying to understand. So it's not a straightforward answer, let's put it this way. And obviously, ultimately, what you want to do is you want to couple it with the weather forecast, okay? And depending on whether today is going to be a cloudy day or a sunny day or what stage of the plant is, have models, just like we do in time control, okay, that's what it will evolve, like just like a plant control, like we that's what we do in chemical plants, for example, like online control, and it will be similar to that coupled with the. So it's quite an interesting problem, by the way. It's quite an interesting problem.
Several levels of optimization required.
Oh yes, absolutely, and more important, understanding both the biology and the physics at the same time, like it makes it quite interesting.
Thank you.
Thank you, Professor Dev. I think Professor Garg, you can ask your question.
Okay, yeah, Professor Agarwal, very nice talk. I think this is something which many of us who work in photovoltaics sort of appreciate, that there's a competition between land and other resources that we want to get from the land. So my question is about when you raise these solar panels above the ground to reduce the shadowing effect. What is the increase in the cost of installation and eventually the cost?
Very, very good question, actually. So it's not viable, right? The cost is very high, right? Because right now the one I showed is 20 feet high in the air, right? And the biggest problem in Midwest is we had to design it for a wind speed of 120 miles per hour, even though it happens once in 5 years or 10 years, but you need to design it for that wind speed. And what that means is the foundation has to be very strong. You just can't just go and put it, right? So what we have done, Ashish, is in the last 5 years, we have been playing with a lot of designs to reduce the height, okay, to bring it closer to the ground. And let's see how they work out. So once we have successfully stimulated the current what we have and we have learned, then our next goal is to stimulate different PV designs and operations, okay, which should enable us to bring it as close to the ground as possible.
Okay.
So that's of course, if in case of corn, or for example in India, Ganna, like, if the height itself is 7-8 feet, you can't bring it below 8 feet.
Right.
Okay, but for the wheat and rice, certainly they can be brought much lower height. Okay, but once you bring lower height, the shadow intensity increases, and then the issue is how do you operate it? Okay, the PV panel, okay, to decrease the interference with the crop.
Right. So in addition to this I like this term agri-electric farming, but in addition to agri-electric farming, nowadays there is a lot of discussion about this BIPV as well as transparent solar cells, because a lot of buildings in countries like India are now glass-based buildings. So as a result, people are talking about semi-transparent solar cells, which allow electricity as well as light to be generated. So what is your sort of take on the BIPV and semi-transparent photovoltaics?
Okay, so the bifacials, certainly yes. Okay, bifacials are very important because they recover more energy. Okay. And but when it comes to the electric farming or agrivoltaic farming, whatever you like to call it, like I believe we were just talking about the cost of the installation, and that's the substantial portion of the cost. Okay, and if you build transparent, why is it transparent? It is transparent only because you're not absorbing all the solar photons.
Right.
In that range. Okay, and if you're not absorbing all the solar photons, that means you cut the electricity production by that factor.
Right.
And so that means your cost has just gone up by that factor. And I don't think that's going to happen. Okay, on the scale we are talking about. Okay, remember if you go earlier part of my talk, large area has to be covered. Right. And the cost must be very low if you really want to do it. Okay, because even if I went and I bought like bed sheets from the Walmart, I still can't cover enough land in an economical fashion.
Absolutely. Okay.
People forget that fact. This energy. Ashish, you're very thankful that this energy is diluted, right? Because both of us can walk out in the sun and just not get burnt. Okay, but as an engineer, if we put our head as an engineer, not as a human being, then this thing is very dilute.
Right.
And so for the buildings, it would be okay, right? Because the buildings, otherwise that window is not being used, right? So it's being, so it's okay for the windows and to have the transparency, because you get the sunlight in the room as well as you get some electricity. So that's mighty good. But I think for large scale consumption, big areas.
Right. Okay. Thank you. I think there are other people who want to ask questions.
Thank you, Professor Garg. I think Professor Shikhar Mishra, you can go ahead.
Hello, Professor Agarwal. It was a really enlightening talk. And just to let you know, I also recently did my PhD from Purdue with Dr. Hyen Wang. And I briefly worked with Scott McClary, your student. But my question.
I just had a big meeting with Hyen Wang yesterday. I spent like 2 hours with her. So
nice.
So you worked on TM, I suppose, ceramics.
Yeah, TM and thin film growth and all of that. Yeah.
All right, nice.
So one of the main challenges that I could see from your talk is that the solar energy requires a lot of land space. But in terms of long-term scenario, so what would be the cost of maintenance of such huge solar panels? Like in terms of, right now we are seeing a lot of water is required for cleaning the solar panels, and especially this would be a challenge in water scarce areas. Or what would be a long-term scenario in terms of recyclability of those solar panels? So just I wanted to know your thoughts about on these directions.
Those are very good questions, by the way. Like, it's just like the maintenance is like in India also, like, with the humid environment and all, people are seeing different issues than for example, a dry place like in US would see. because of the, the corrosion and a lot of corrosion issues with the joint, with the soldering and connections and interconnects, and there are many issues. And so the maintenance is an issue, and that makes it exciting, right? Because what that means is that what should a PV panel look like in the Indian context is a subject of research by itself, right? Because of course, this what is being developed here is more in the context of what works in this part of the world. So, which is so I find that quite exciting, actually. That things are different, meaning us researchers have a job to do. Okay, and but as far as the maintenance is concerned, your point is very well taken. But one thing I would like to say though is if you do install PV panels on agricultural land, the maintenance cost does go down. Okay, because just it is distributed equally between, you're already taking care of the land, right? And PV happens to be just there. It is not on its own where you have to build the infrastructure to maintain it. Okay, the same farmer who is maintaining the land will maintain the PV panel. Okay, so all the studies done so far, the cost is substantially reduced for maintaining it. So because you don't have to build a new water connection if you're cleaning your PV panel with water, right? Because you already have water to supply to the plant. Okay? And if you do water PV panel, that water can still be used for the agricultural land.
Yeah, I mean that makes sense.
Okay. So there are many issues which really, interconnected issue on the maintenance side, actually. So that's what I would say.
Right, yeah, thanks.
Thank you, Professor Shikhar. Professor Kanwar, you can go ahead with your question.
Okay, yes. Hello, Dr. Agarwal. Very nice talk. I myself work on solar research, solar panels. My area of research is on perovskite solar cells, but I've worked on organic solar cells also earlier. So very interesting talk. I like the part where you talked about agrivoltaics, especially. So I had you touched upon this just briefly, right? That in agrivoltaics, you can. There's an issue of, especially in the case of India, right? In US, it's not that much of a case where panels, they develop a lot of dust on them over a period of time, right? And this dust accumulates, and that lowers the performance of the panels, right? Your transmission goes down, your efficiency of the panel, I mean, the electricity that it generates, that also goes down over time, right? So there's a need to clean these panels periodically, especially in Indian scenario where there's a lot of dust, a lot of wind blows, right? If you see our panels outside, within 10 days they accumulate so much dust that it becomes like the panels, they work like 20% of their efficiency compared to the clean panels, right? So there's a need to clean these panels periodically. So with this agrivoltaic solution, right, you were talking about that the water that we use for irrigation, right? The same water can be used for cleaning the panels also, right? So you have one stone and you're hitting two birds, right? Can something like that can be adopted, right? Is it easier to do? Like you use water to clean the panels and then the same water can be recycled for irrigation for the agriculture?
So one has to look into that. There are many ways of doing that, actually. But I do not know how in the Indian context that would work out. But the catch is that certainly, the multiple solutions which one can think of, and there's a need to sit down and to say, okay, in the Indian context, what will work, okay, and how do you collect that water which you are cleaning the PV panels?
Because
and
in India, this is
right.
Like,
so at the
easiest.
At the very least, imagine, if you come to US, right, the houses have these gutters, right? The rainwater is collected along, right? At the gutter, just simple low-cost gutter, right? It's just aluminum hanging at the end of the PV panel. The water you put is collected, right? And then you can just rechannel it. Yes. Just like here, the water is from the roof is rechanneled to the waste, right? Okay, and so there are many simple solutions, okay, and very cost-effective solutions actually. To use that water again, and it can be very complicated also, by the way. You could install sensors, direct water at different places. So from being very simple to very complex, and so there's a whole spectrum of solutions in between. And I do not know, what will work best in the Indian context, because I have never worked on a case in India. Okay, I've never, I was a shahar ka ladka, I grew up in a city, urban, grew up, came to Kanpur, came here. So here I've been working on the farm now with my agriculture colleagues. So I'm getting some flavor of the agriculture in the US, okay, but I have zero flavor of agriculture in the Indian context. So I really do not know, unless I go there and spend a time and,
Yes. So I also, because I see the panels outside and they collect so much dust, and then I ask myself, like, how do we maintain these? How do we maintain these economically? How do we do this periodically without recruiting dedicated manpower who does that? Right? So there are things that we need to figure out.
And Person Allah, it has to be also done very carefully. I can't just take a bucket of water and a brush and go do a date, because then, because pretty soon the surface will be rough, and all the light will never reach to the, you will form all those patterns, and with the brush, it scratches, and all the light will be gone. Like
you don't want to damage that.
Yeah. So it has to be very carefully washed. There are people who have done a lot of research in how to wash TV panel itself. Like it's not a trivial, because in the old days people will go with a broom and just boom, 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 and then suddenly you realize that you destroyed the whole panel. So yeah.
Thank you so much.
Sure.
Thank you, Professor Kanwar. Professor Lalto, you can go ahead.
Just have one question. What is your view on the future of hydrogen energy generation by solar thermal route or the heat-based hydrogen generation? What is the view on that? The future.
So that's So by solar thermal, you mean directly using the solar energy as a heat through concentrators and then do that, right?
Absolutely, absolutely.
So I was very fascinated with that, by the way, in from 2013 to 2017. And I have published a couple of papers too, actually, on that. But one of the challenges with that, what I found was, and I do not know, if probably that might be even more a challenge in the Indian context, is the solar irradiation. What fraction is direct versus what fraction is diffused? Okay. And the question before you was the dust on the solar panel. That's an indication, direct indication that the diffuse light is quite high, because if there's too much dust in the atmosphere, and if there's too much dust in the atmosphere, that means the light as it is traveling is getting diffracted all along, and the direct component of the light is small. So unless and until, for the locations where the direct component of the light is high, okay, like it may not make that much of a sense, and those calculations can be done, like in the sense that if 50% of the light is direct and 50% is diffused, then if I put a solar thermal hydrogen, then it's only 50% of the light I'm working with, and if I'm working with the 50% of the direct light, and if my efficiency is 50%, then I get only 25% of the solar radiation as as the hydrogen, or if that efficiency is only 20% to hydrogen, then I get only 10% of that, right, as a hydrogen of the solar energy. On the other hand, a PV panel will work with the entire spectrum, and if it gives me a 20% efficiency, and then if I use an electrolyzer which is 12% efficient, then I get to the same number, like 12% efficiency of the hydrogen. So I think, so the more I have thought about it, and that's why I've been shying away a little bit from that. But if the direct component of the light is very high, then certainly that would be a good thing, worth looking into. Okay. But also, like, as long as you can find materials for those high temperatures which are involved, right? Like the temperatures really approaching 1100 degrees Celsius, from anywhere between 800 to 1100 degrees Celsius, like those high temperatures itself brings an exciting material constraint. But nevertheless, I think, so I've never sat down and looked in the Indian context as different locations, the diffuse versus the direct light. Okay. And that would be the major issue in my mind.
Okay, thank you.
Maybe we can have a last question from Sarang.
Professor Agarwal.
Yeah. Hi.
So when I saw the pictures of solar panels raised about 20 feet above the ground, I just run imagination that we may have a floating farms, solar farms, but that is a distant dream. But then coming to the ground, so why don't we consider covering highways instead of agricultural land? Because
Sure.
there also you have to have a framework for installing solar panels.
Yeah, if people are looking into that too, certainly, Sarang, yes, okay. But again, is that area enough? Okay, would be the question. Okay. And of course, on the side of the highways, like, and that would be like, the urban areas I was talking about, 10% coverage, that would be included there, I think. Okay. Because you can put on the sides of the highways, certainly, yes. Okay.
Yeah, over the highways, actually, not the sideways. I mean, over the.
Yeah, over the highways too. Yeah, you could certainly do that too.
Maybe one benefit I see, people will have to use less AC in their car if they are driving their cars in a shaded highway.
Yeah, but again, it will probably on the highways, probably because the trucks probably it will have to be built again high enough, and because the trucks, if you have to build, because trucks will decide the height really, not the cars, and that height could be quite substantial, like 20 feet for sure. And I know from my own experience, 20 feet high PV panel is very expensive. I can tell you that for sure. Okay, it's quite expensive. Okay, it's I think Ashish asked the right question. That height is not sustainable. Let's put it this way.
So I understand that having solar farms floating over the sea is not practical at all, right? Is it right?
Corrosion.
Corrosion.
That water is not the friend. That seawater is has a lot of cats and dogs in it, right? So
because that is a good option, because you just use the water there and wash the panels.
Yeah.
Okay, thank you.
But you know what, Sarang, the good thing is we have to use all our creativity. Where can we install it, and rather than laying them on the side? So I take my answer back actually. Like, yeah, sure. Like what is in the book which says that we can't develop materials which can last on the ocean. That everything has a counter. One has to think like maybe it is a good material research into what goes into making those things.
Okay. I think we've taken a lot of time in questioning, answering, and
Thank you,
Professor Agarwal, for a wonderful lecture.
Professor,
very quickly, okay? Very quickly. You have to mute yourself. He's professor from IIT Kanpur. So,
yeah, I could not find the handwriting icon here. That's why I'm turning the video on and trying to do that. Anyway, Professor Agarwal, excellent talk. Very, very, very excellent talk. Thank you very much for. I get a lot of yarn from this talk. But I have two things. In fact, Sarang, whatever he asked, I also had the same thing. Railways and highways are what we have. India can cover a lot of space in that, because 11 watt per meter square is what is the minimum you try to calculate with the silicon ones. And another one, what I'm seeing is for the whole entire USA, you've calculated something like 1665 gigawatt per meter square is the requirement. But this site, suppose it is considering winters and everything put together, or suppose if you go to the Indian case, bright days are much more, then is that going to matter your calculations? Or
No, actually that watts per meter square is not going to matter at all, because that watts per meter square with 1665 gigawatts per meter square, which you're talking about, that is the need of the country. So you take India as a whole, okay, and take different sectors in India, okay, where the energy is being consumed, okay, and you look at the end use, okay, and then you say, okay, this is the total energy India, not energy, like total end use, which shows up constructively, shows up, okay, and so what is that in watts? Okay, so basically translating that annual to per second, okay. So and that's the use, and the way we did the calculation was we did not want the fossil. So we know how much fossils is used. We did not want to directly translate that to gigawatt per meter square, because that number is the wrong number. Because in automobiles we are using 100 units of energy, but it doesn't show up as 100 units of energy. At the end, it is only 15 units of energy, which is really gone to useful work. But if you gave me electricity, then electricity can be 75% efficient with the same thing. So I would need 1575, 1/5 of what I'm putting with gas petrol. I need only 1/5 of that from electricity. Okay. So I have to account for that. So in a solar world, I will need only, so whatever the automobiles or trucks are like 25% efficient. So, so again, if you're doing it this, what is, so because the end use is the same, not that the fossil is, that energy is the same. So that's why we had to do those calculations.
Yeah,
and
yeah,
I said,
but
my
still-
graduate student has done that for India, by the way. My graduate student has done that for the India, except that he's making PV panels, he's experimentalist, he's making solar cells. So once she's making solar cells, so I never encouraged him to publish it. But maybe after this, after today, maybe I will go back and say, hey, Shwashi, why don't you pull it out and let's you know, he should publish it. It's my mistake, actually. It's my error. I should have done that.
So it matters, right? The bright days and bright places and places like US, you have a lot of winter and you have no sunlight some of the days. So considering that PV requirement for India will be, you know, I mean, you can still work out with the PVs, just with the PVs as well.
Sure, absolutely. So you're totally right. So what that means is, but the gigawatts per meter square of the country use will not change. However, what will change, okay, is the how many watts per meter square being produced from the solar farm. So that number, so the number will be more close to 10 and 11 rather than close to 5 and 7.
Right. Oh, excellent. So yeah, all these things taking into consideration the whatever the program that is going to come out will be excellent. It will be used by many people. The calculation, whatever you are trying to do, you know, the entire program which you are developing, that will be excellent.
Yeah, so we have already published it. So I have to be truthful. We're not doing any more calculations of this kind. It's already published. It is already out there. At least for the US, it is already out there. It provides a template to you know, if anyone wants to do it for another country, there's a template to it. And as I said, I've even lost interest, as you could clearly see, because you know now we're more focused on. I'm more focused on FSIM models now to how the agriculture, you know, the photosynthesis, trying to learn. A chemical engineer trying to learn about the what I call the crops, and you know, so it's like being a perpetual graduate student. I've never left Kanpur. Okay, I'm always learning. It's like it's you know, against the grind all the time. So learning, you learn one subject, then you have to learn the other one, and then you have to learn the other one. It's a continuum battle.
Absolutely.
Learning is continuous. Learning is continuous. Thank you.
Learning to learn. So with this, we have we'll close the session. We thank Professor Agarwal for sparing a lot of time with us, and you know, from his very busy schedule. And Professor Agarwal, as a token of our appreciation, on behalf of the center, what we have done is we have created a Chandrakanta Keshwan Grove in the memory of Dr. Chandrakanta Keshwan, and where we plant trees in the name of every speaker that we invite to our lecture series. This is just to prevent the wastage in the form of material gifts. So, and this 14 trees site, actually the motto is that a person, if he or she plants 14 trees in his lifetime, then he or she will at least offset his or her own carbon emission. So this is just our small contribution in your name, if you don't mind, at 14trees.org. We will send you the details of this tree. So there is a dashboard of this tree in your name at the site, and we will send you the link, and you can monitor the health of the tree online.
Okay. Thank you very much.
This is our small token of appreciation for your time, for your wonderful lecture. And we look forward to, of course, you are on our department's advisory board and also as a distinguished visiting professor in our department. So we hope to have very long-term interactions with you in the future. And of course, I look forward to seeing you in Purdue very shortly.
Same here, same here.
Thank you.
I have just curious question. Maybe we can stop recording and I'll just ask. Go ahead, ask. Why not Why Amwa? Like, you know, you have written like